What's up, guys? Welcome back to another YouTube video. So in this video is basically the part 1 of creating this diabetes prediction app. So yeah, it's a graphical user interface that basically helps us predict if a person has diabetes or not. So in this video, we'll be majorly creating the actual model, right? Writing the code. While in the part 2 video, we'll be using Streamlit to create this interface. In this part 1 video, we'll basically be using Scikit-learn, Pandas, NumPy, and Jupyter Notebook, where we'll be writing our code to create a model that will help us using a diabetes data set, which will be provided in the link below, to create this diabetes prediction app. While in the next video, we'll be creating this graphical user interface. So a little demo would be just enter the glucose value. So I'll just say 100, 100, blood pressure, 43, skin thickness in milliliters, 23, insulin, 5, body mass index, 25.5, diabetes pedigree function, 0.7. There are explanations for all these values will be provided in the video to come. And age, let's say 23, right? Age, let's say 50. Let's say 50. Oh, sorry, that's too young. Let's say 35, right? In terms of predict diabetes, so this patient does not have diabetes, which is a good thing, right? So yeah, a simple diabetes prediction app. So stay tuned and let's start coding this part 1 video. Make sure you like and subscribe. And yeah, let's get started. Open your web browser. Get an Anaconda Navigator. Yep. Download. So we just get the community edition. Download now. So since I already have mine, follow all the default setups, then you should have something like this pop up. So Anaconda navigation basically comes with some necessary tools we need for Python. So in this case, we'll be using PyCharm and Jupyter Notebook. So Jupyter Notebook to make our model, while PyCharm for Streamlit. Okay, so while PyCharm for Streamlit. So we'll just come up here. And launch our Jupyter Notebook. So it should take you to a web application on your default web browser, which is Google for me. So it should be like your file explorer, right? So I'll just come to my desktop here. So I can see I still have my basic desktop. So since we're working with the dataset diabetes, I already have that CSV file, comma separated values. So I'll drop the link in the description below. Download it, but you can come to this website called Kaggle. So Kaggle is basically the common or basic website for data scientists who can get data sets, different models, competitions here on Kaggle. So you can just come to the data sets section here. You can search for the diabetes data sets. You can just say diabetes. Should probably be this one. So whichever one is the most similar to the data set we're using. So I think it should be this skin thickness and insulin BMI. Yeah. So it's all about the outcome. All right. So we're basically trying to predict if a person would have diabetes or not. And we're going to use a graphical user interface to display that. Okay. So yeah, after downloading my Anaconda, I can just close that up. So now back to my Jupyter Notebook here. So on my desktop, I'll just create a new file. I can just come here, new Python file, right? It's taking me to a whole new web page. So let's load up a bit. Okay, so quickly I can just edit this. I can just call it data diabetes model code. I can say diabetes model code or IPYNB. Okay, so for those, so I have my Jupyter Notebook file. So there are two major Python frameworks that we need whenever we're performing data analysis, data science, or anything machine learning, AI, artificial intelligence, something like that, right? So they are NumPy and Pandas. So NumPy is basically numerical Python. NumPy, numerical Python. Basically deals with all the numerical aspects, not anything numbers, mean, median, mode, things that you don't have to write your own standard functions for. Very, very advanced. We also have engine values, engine vectors, stuff like that. Very, very advanced. Lane space, stuff like that. Alright, so we're going to import the packages. Normally, you don't have to install it because it comes by default. But if you don't have it, you can just pip install NumPy. So by default, everyone should have that. So I'll just say import NumPy. We're going to use an alias here because we don't want to type in NumPy every time we want to use a function or a class inside this NumPy module because yeah, it is a module. So I can just say NumPy as, so an alias here, we say NP, which is the most common. And we also want to import pandas. So say pandas as PD. So pandas deals with data sets, data frames, series, stuff like that. Basically structured data, basically in a form like that. So we have different methods, functions, things we can use to organize, structure our data basically. So that's pandas. They're the two most foundational Python frameworks for machine learning, data science, data visualization, and stuff like that. So now that I've imported the two, let's just run that. So to confirm that they are modules, I can just say type np, alright? So np is still NumPy, it's just the name I'm giving it to you. So I have it to be my module. Okay, so now let's import our data set. So our data set is in that comma separated value, the CSV, which is dataset underscore diabetes. So I'm keeping it in the same structure, so I won't have to write a full path, right? So it's in the same directory. So it's dataset underscore diabetes or CSV. Of course, you can rename it to something else. So I'll just say data frame. So I'll call it df, the name of my variable, right? Should be PD. So inside my pandas module, right, I have a function called read underscore CSV. You can see it's a CSV file, comma separated value file, right? I can open with Excel team. So read underscore CSV. So we know the tab or tab function. We know what tab does, right? After you tab dots, we can also check tab. So tab basically suggests different methods, functions, classes, and stuff. You can see C for class, F for function, I for instance, stuff like that that we have in our module, right? So it's not like VS Code that's automatically suggesting. So the IntelliSense is a bit slow, if you ask me. So just say PD dot. So I can go ahead and type read the underscore and suggest different reads. So you can read Excel files, HTML files, JSON files, stuff like that. But working with CSV, it's also read CSV. All right. Go ahead and right here, I'll just type data sets or data sets underscore PTs. You don't actually need to specify it being a CSV file, but just to be on the safe side, specify it being a CSV. Okay, so just to be on the safe side, I'll specify the .csv. Okay, so running this, I've stored this data frame inside this variable df, which means data frame. Okay, so it is a data frame, a structured table that holds different columns together. It's basically like a table, an Excel table, right? So something like that. So we can check the entire table, but it might be a lot of columns, a lot of values and stuff. So we just want to see a little bit of that data set. So there's a function in our pandas. So if you're familiar with basic OOP in Python, I will know that read, okay? I will know that this df has become an instance of PD. Why? Because read CSV is not just returning any value, it's returning an object. Alright, so I can shift tab to see what it does. So docstring, so shift tab here, reads a comma separated value file into a data frame. So it's basically returning an object of a data frame. How can we confirm that? I can say type df. So I can see it has become an instance of the class data frame. So this data frame class is inside a module frame, and this frame is inside another module core, and this core is finally inside our big model pandas. Okay, so that is where our data frame comes from. Okay, so we have that. So df is an object, right? And every object can have different methods, right? Methods, fields, values, properties, whatever you want to call it, right? So we're working with a method head. So a method, since df has become an object or instance, any function there becomes or is called a method, right? So the head function or the head method, sorry, automatically returns the first five rows in our data set. So the rows are the horizontal values, right? So if I run this data frame of head, automatically it's going to show me every single, oh my god. So automatically it's going to show me every single column. So it means I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically I have 10, but I have 10 columns here, which is quite similar to the data set we have here. Outcome age, I think is the same data set. So you could have just downloaded it right here. All right. So yeah, I have these 10 columns, but these are not the entire values because I'm only getting the first five. The 0, 1, 2, 3, 4 is actually the first five values there, right? So you can pass an argument here to specify how many, but by default it just returns the first five. So I could have said to return the first two, 0 and 1 column, or row 1 and row 2, which is index 0 and index 1, right? By default returns first five. Okay, that's good. So now I want statistical information about this data set, right? Or this data frame. Since we converted it to a pandas data frame, right? So we have two methods we can use here, info and describe. They're quite similar if you ask me. So if you see info tells us, okay, it's an object of class data frame which I've seen using type. It ranges from 2000 and it has 2000 entries from index 0 to index 1999. So printing out the data frame alone would show me 2000 entries, which is quite a lot. And I just checked the first five, right? It's quite easy. So we have 9 columns or 10. Do we count 9 10? 1, 2, 3, 4, 5, 6, 7, 8. Oh, it's 9. So we have 9 columns, right? We have 9 columns. So you can see the importance of checking the information. Data types floats. So non-null means, oh, it's not empty. No, 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 no. We have data type integer 64 bits float. So our BMI and diabetes pedigree function is actually float. When working with a data set, it's actually good to understand what we're working with. So in this case, we're trying to predict if someone has diabetes. The pregnancy, I think that one's quite straightforward. How many pregnancies, stuff like that. Would that be women or men might be included? Glucose, probably sugar level, blood pressure, skin thickness, insulin, BMI, body mass index. So diabetes pedigree function. So let's just see what that's about. See diabetes pedigree function. You can see is a numerical measure that quantifies the likelihood of a person having diabetes based on their age and family history. So it's also basically helping us predict if someone has diabetes or not based on their family history. So based on inheritance, stuff like that. So the higher your diabetes pedigree function, the higher the likelihood of you having diabetes, something like that. So it's more linear, if we say, right? So we can see it's probably going to be from 0 to 1 year. Things like this just range from 0 to 1. But if you convert it to percentages like 12%, 23%, 63%, and so on and so forth. So we have the age and we have the outcome. Okay. So the higher your age, the more likely you have diabetes. So I think this should be a real data set. So another important thing is the data scientist, machine learning engineer, whatever we need to do is you need to understand the sector or the field in which you're working with. So you always need to understand the context before trying to predict something. So that's how we made that research. Now let's go back to coding. So I'll say df.describe. I want to check out describe too. So let's see. Describe returns more of statistical values. Counts. So everything has 2000 values, right? Yeah. the mean of all the pregnancies. So the average means more of like our average. So the average number of pregnancies of every 2,000 personnel is 3.7. Or let's just say 4. Glucose, blood pressure, stuff like that. 0.4 degree per degree function, age, outcome. Yeah. Alright. So our standard deviation, mean, minimum, the smallest value is 0. So the smallest number of pregnancy is 0, obviously. There's no negative there. Stuff like that. Smallest DPF, the youngest person there is 21. So you can see we can get basic statistic information. So imagine having to scroll through the entire 2,000 entries just to look for the youngest person. Well, we could have just done this. All right. So 25% of people, 50% of people, 75% of people, the maximum. So someone has actually had 17 pregnancies. That's quite a lot. 17 pregnancies, right? And degree pedigree function 2.4. Wow. Age 81. That's quite young, if you ask me. So yeah, the outcome is basically just yes, no, yes, no. You have pregnancy or you have diabetes, you don't have diabetes. So yeah, out of all these columns, out of all these 9 columns, right? The first 8 are helping us check if this person has diabetes. While this last one is basically the answer in our diabetes. So in any programming aspect or IT world, 1 mostly represents true and 0 mostly represents false. Whether in our statistics or in basic programming and stuff like that, right? So 1 usually represents true, 0 represents false. So if you're familiar with programs like C, you know that 1 true, 0 false, right? So now let's start with our actual coding. So we'll be using Scikit-learn as our Python framework for this machine learning algorithm. And we'll be using logistic regression. Yeah, let's use logistic regression. Why? Because logistic regression is more of a classification program. If let's rewind that a bit. Let's rewind that a bit. Under machine learning, right? We have, let's just say we actually have 4, but most people like to classify into 3. 3 types of learning, right? Machine learning. The ability of a machine to perform like human beings, right? Supervised learning, unsupervised learning, and reinforcement learning. There's actually something called semi-supervised learning, but not too common, right? So supervised learning is basically you feeding the machine learning model, the machine learning model that's going to perform certain actions, right? Call it the model. Is you basically feeding it labeled data with information. Just imagine in your kitchen, right? You have different cans, glass cans that have labels saying, oh, this is salt, sugar, this is seasoning, this is rice, stuff like that, right? You're basically feeding it labeled data so it can cook, so it can do its own thing, right? So it can predict for us, right? That's supervised learning. You keep feeding it a lot of training data, but not too much, not too little, just the right size, right? And we have unsupervised learning. So unsupervised learning is basically you feeding it data but not labeled. So the machine learning model is going to have to work, it's going to have to study it, analyze it, and see how it works. While reinforcement learning is basically just the machine learning model understanding the environment and basically looking to get rewards. So it's more of a reward system, right? It's quite advanced. But for now, we're going through a supervised learning. Why? Because we have labeled data, right? We know that this is pregnancies, glucose, blood pressure, and we're giving it data, or we are going to give it data. All right, so let's come back. And under supervised learning, which we're using, there are 2 basic problems, a classification problem and a regression problem. The classification problem is just simple thing. Yes, no, 1, 0, boy, girl, something like that. Binary, something binary, this or that. Okay? So, which is what we're doing here. So we have different algorithms to solve a classification problem. So the most basic or common one is logistic regression, which is what we're going to use to solve this problem right here, right now. So, and all these algorithms mostly come from Scikit-learn, SK-learn. So say from SK-learn, So I don't just want to get everything there. I just want a particular module or inside this package or bigger module Scikit-learn, right? So from Scikit-learn dot what's linear model import logistic regression. Alright, logistic regression. So now we're going to create our model. So model is basically just an instance of this class, right? It's basically we already have the foundation down. We're basically just going to create a variable or an object that is going to be an instance of this class, logistic regression, right? It's already a class now. So I can just say LR or my model, or let's say logistic regression model, LRN, right? LRN equals logistic regression, right? Simple way to create an object in Python, not too stressful. So let me use my tab again, finish it up for me, right? As easy as that. So I already have my model. My kernels will be slow. So I already have logistic regression. I can just say LRN dot tab. I can see different methods, classes, stuff and stuff that I have inside. All right. So the two major functions that we'll be using, it's quite saying unknown here, don't know why, are predict and fit. So we use fit to basically train our model and predict to test our model, right? So now, how are we going to train our logistic regression model? Before training and before predicting, we need to particularly split our data. First of all, into the data that we're going to use to train it and the data we're going to use to test the model to see if it actually worked. Because we know that these guys here are the real values of data sets. It's an actual correlation of information that forms this data set, right? So we need to use a certain number of rows or entries to train the model. So when it sees, so it's basically analyze this pattern. Oh, so to basically analyze this pattern and say, okay, this particular number of pregnancies with the glucose, the blood pressure, with the skin thickness, insulin, BMI, degree per degree function, age, stuff like that, it will find a midpoint, right? And know that, oh, or this certain, or what would you call them? This certain pattern decides whether someone has diabetes or not, right? So that's all we're going to use to train. And since these are actual data, we also use few entries to test if this data set actually worked. And then we'll check our accuracy and stuff like that, right? Good. So we're using another function from Scikit-learn, Scikit-learn, which is our train test split. Okay, from Scikit-learn, this time from module selection. So over time, it's quite easy. From module selection, import what? Import train. So it's a function test underscore split, right? So import this from module selection. Everything okay. So I can just type out my test function here. So train test split, right? So my bracket is a function, right? So I'll shift tab on it to just see the documentation, see how it works. So I advise you to basically do this every time you see a new function. Just get the doc string, try and understand it. There will be examples and explanation of the different arguments or parameters there. So basically, split arrays or matrices into random train and test subsets, right? So basically for models like this. Right? So the arguments needed there, we actually have your array where what you're actually splitting our data set, which is our DF, right? So test size, the train size is not really compulsory. So we just need one thing, which is just our test size, right? We need to specify one of them. So test size between 0 and 1. So 0 representing 0%, 1 representing 100. Same for train, random state. So random state default is none. It's not really compulsory, but it controls the shuffling applied to data before applying the split. So just a random number that helps you shuffle the data set. Okay. So nothing too serious there. You have shuffle true or false. Do you want it to shuffle or not? Stratify data is split in a stratified fashion using these as the class labels. So, yeah. So you can see an example here. So escalate the model selection, how we've imported it, right? So I can just copy the example here. All right. So good. Now, if you're looking at this, so see, oh, I didn't copy it that well. Train test split. Do that again. Shift tab. Just come back down here and copy this. So paste that down. Control V. Good. So now we're looking at it. We'll ask ourselves, where does X come from? Where does X train come from? Where does Y come from? Right. So if you're familiar with unpacking of variables, right? Let me just escape here and then press B to create a cell below. So if I have an array basically, right? Let me create the two variables A, comma B, right? And I have an array of 1 and 2. So Python's feature basically unpacks this array and splits or distributes the values in this array or any iterable contents, basically lists, array. Okay, this is a list. Sorry, lists, tuples, not necessarily dictionaries, but you get the flow, right? So things like that. So it basically unpacks this. So it makes A get assigned to what's 1 and B assigned to 2. So just print A and B just to check real quick. I see A is 1 and B is 2. So this Python's unpacking feature, right? An easy way to create variables without having to, write multiple lines, comma. So, but we still need our X and Y. So I basically want X to be everything I'm going to use to get my answer, right? Which is outcome. And I want Y to be my outcome, right? My answer. So I would say X, so capital letter X, that's just the ethical conventional way of doing it, right? So X should be the data frame, right? But not everything in data frame. I want to remove outcome. So, just like objects like dictionary, if I want a particular column or field or, colon, basically a colon in our data frame or dictionary, I'll just say df of that particular column, right? Glucose. But since I want multiple, I basically want pregnancy is glucose, all the way to or except outcome, right? I'll put them in a list, but it's too much to type. So there's a simple method that just helps us remove what we don't want, which is outcome, right? I'll just say df.drop. So in this case, I don't want outcome. So it's basically going to select everything aside outcome. All right. So df select outcome. So I need to pass axis 1. Axis 1 basically means for every entry, for every row then. But we can check that again using our docstring. So drop basically drops selected labels from rows or columns, right? So rows or columns, but I'm specifying what's rows. So remove it from rows. So axis 0 or 1, index or columns. So I'm specifying columns with 1. So I'm moving column, what's column outcome. So the default is 0. So that's what we have to specify, column axis 1. Okay. So that's drop outcome axis 1. So that will be our that will be our X, sorry. And our Y would be just our outcome, right? Instead of the drop, I don't have to, if I'm using drop now, I'd have to write out everything, right? So in this case, I'll just select outcome. Since Y is just the outcome, right? Simple dictionary, indexation, something like that, right? So now I have my X, now I have my Y. So X is everything aside outcome, while Y is the outcome itself. Okay, so now I have my X and Y. Okay, so now we'll come back to this cell here and we can understand it way better, right? We can see train test splits takes the X, alright, and then the Y. Then test size basically from 0 to 1 is basically saying how much percentage do I want to assign as the testing size, right? So that's 0.33 basically means that 30%. I can just make it 30%, right? So automatically to be 70%. So I don't need to write train size if I'm already specifying test size. Same goes for train size. Test size is way more common. It's random number that will help us shuffle it or arrange it basically. Alright. So having random state basically says shuffle is set to true. Okay. So yeah, so from the unpacking example we did, we know this is returning an iterable, preferably a list in which the first value there is for the train, for the X train, second value is for the X test, then the next Y train, Y test. So remember what X is. X is everything before outcome. Then the training is okay, what we're going to use to help our model understand the flow. Then the test is what we're going to use to test the model. Y train, the answer for training, right? So that it's used to keep track and stuff. So it basically says, okay, this particular set of X values leads to diabetes or not, stuff like that. So the test is what we're going to use to test our model later on. Okay. So just run it with Shift Enter. I don't think I've said that before. So use Shift Enter to run actually, or you can come up here and use this run the cell above, which is also Shift Enter. Okay. So sorry about that. Shift Enter, and that has been run. So you can just check X train here. So it's head, remember. Check the first 5 values. So Shift Enter. We can see randomly distributed numbers. You can see it's not in order because random state has shuffled it, done it anyhow we like. So 836, this is the first layer in our X train. Someone with 6 pregnancies, glucose 124, skin thickness 0, age 29. Obviously, we're not going to see the outcome, whether that person has diabetes or not, because this is our X. Remember, X doesn't have outcome, Y does. Okay, so comparing the X value to the train. So based on, not everything, right? Go ahead, just a few. So based on these X values, so 836, this person 836 has diabetes 1. So that's 1 here. Okay, so yeah, this is basically our train data set. So we'll use the test to test our model later on. Now let's actually train our model. Simple method, fit. So just use the fit method on our LRM. So say LRM.fit, right? So fit, let's check that out again. Shift tab. So fit the model according to the given training data. Alright. So let's see how it works. Just basically takes X and Y. So X, Y sample weights not compulsory. So what does sample weight mean? Array like of shape and samples, array of weights that are assigned to individual samples. If not provided, then each sample is given unit weight. So basically when you reach a stage where you need to give bias, meaning some particular data have more weight, like have more importance, in your scale of preference, have more importance than some other values, we use sample weight to distribute such. But by default, everything is given same importance, same weight, no bias. So that's that. So just pass the train and the Y. So I could have passed X and Y alone, but remember X and Y basically holds the whole 2000 entries. Now basically I'm training my model with everything. So how will I test it? Which is why I'm using X train and Y train. Alright, so train our model here. So if I just run, so okay, it's just a warning, no issue there. Print the number of iterations, no data there. They run. I still have my logistic regression. It has been trained. Oh well, I'm going to run it again to check. So my model has been trained. So now my model understands the flow of how everything works. Okay. So it has scanned through. I wonder how many. So 70%. So I use 70% to train. So 70% of 2000, that should be 1400, something like that. So yeah, I think 1400 for that's 1400 entries that we used to train, about 600 for the test. So now that we've trained, all we need to do is test. Let's see how good my model is. Alright. So create a variable called predict. Alright. The predict is basically the function or the method of our model that we use to get a prediction of our answer. So it's that easy. Alright. So I'll say LRM.predict. Now what am I predict? I basically just want to predict all the X values. Alright. All the X values. So I'll say X underscore test. Alright. So I want to predict everything here and get their results, right? So if I run this and I check my predicts, I can basically see everything. So it's basically predict returns an array of numbers, basically, or a list. Yeah, it should be an array, not a list. Quite almost the same thing. So yeah, an array from NumPy and stuff. So you can see 0, 1, 0, 1. So basically the first person here, so there are people, right? So the first person in our X test doesn't have diabetes. So let's just check my X test here. So X test, let me just see head, the first 5 people, right? So this first person in X test, remember this is X test, 4 pregnancies, 1 glucose, blood pressure 72, GPF 1.39, age 56. So the person doesn't have diabetes. The second, same different values, person doesn't, but the third person, it's not sure. Remember, it's not sure. It's just a prediction. But yeah, we'll check how accurate our prediction is right now. So you can see 8, 179, 72, skin thickness 42, insulin 130, stuff like that. All right. So we have that person has diabetes. So now, but every value here is still quite structured. What do I mean? It's basically the data set I downloaded that I just use to train it and to check my prediction. Now I want to use values of my own to check if a particular person has diabetes, because now I have a model that knows, or that knows how to check, that knows how to predict if someone has diabetes or not, right? So now let me actually test it out. Let me predict it using my own values, not just values I got from the data set, right? So I'll just say create, let's just say, okay, let's use a cool, let's write a simple function, right? So we'll take def as diabetes. Let's call it has diabetes, right? So has diabetes will pick an array of what, or a list, stop saying array, right? So a list of PR, let's call PR pregnancies, right? Then GL for glucose, BP blood pressure, skin thickness, ST. Instead of an array, let's just pass it directly like this, right? Then ST, right? Then insulin, IN, that's keyword, INS, BMI, then EPF, and age, right? So yeah, these are the things we need for a function. So you don't need to put in the function, but I just want to do something to make it cool and nice, right? Since it's just going to return 0 and 1. So we're going to use control flow later on. So basically, yeah. So after collecting those values, right, I'll then say LRM to predict. Remember, LRM to predict method basically checks or predicts for us, right? Just calls the predict method. So since I have multiple values here, I'll pass it as an array, right? Pass it as an array or a list. We'll just basically pass everything again. PR, GL, BPA, ST, INS, BMI, PF, right? Age, right? All that. So basically predict that. So let's start in a variable. Let's say answer. So answer is going to be either 0 or 1. Based on all these values, it's going to be either 0 or 1. All right. So I'll use my simple if statement here. So I'll say if ANS equals to 0, right? So if it's equals to 0, print what you have diabetes. Fortunately, so let's add a nice emoji there. That's sad, yeah, sad emoji. So you have diabetes, not good news, right? Then elif, so if not, or just else, let's just use else. So automatically 0 or 1, right? It's not going to be any other value. So the other value is obviously 1. Oh, sorry. 0 means you don't have diabetes. So 1 means you have diabetes. So if answer is equals to 1, it means you have diabetes. Well, that could have messed up the whole function here. While print here, I'll say what you don't have. So 0 means you don't have, which is a good thing, right? You don't have diabetes. So Windows dot smile emoji, I guess, yeah. Smile emoji. That's it. So I have my function, right? I have to call the function. Let's test it out. So has diabetes. So the function I just created right now. Now let me pass PR. So pregnancy, we're creating our own values in our head right now, right? So this is someone that has given birth twice. Glucose number. How does glucose number work though? Let's quickly check that out. Glucose value meaning. Let's see what the value actually means. In the case, the amount of glucose sugar in the body serving as the body's primary energy source. Between 100 to 125, what's this? mg megagram. Okay. It's basically the amount of sugar in the body. Okay. So it has its own units. So let's check what this unit is. mgdl. Milligrams per deciliter. Okay. Milligrams per deciliter. So we have that. Nice. So 100 to 125. So I guess 90 is not stable enough since the average is 100 to 125. So let's see someone that has a stable glucose, right? Let's say 110. 110. All right, blood pressure. I think we're familiar with blood pressure, the pressure of blood, right? Something like that. So zero, how does someone have zero blood pressure? Blood pressure, let's check. Blood, so we need to understand the values too. Blood pressure value meaning, right? So represents the force of blood against the arterial walls in the given as two numbers: systolic pressure, the top number, when the heart beat, and diastolic pressure, the bottom number. So yeah, I know it's like by 120 by 80. So if we're just using one value here, is it the average? Okay. So let's just say we're using diastolic pressure, since diastolic pressure seems like the higher one, 120, right? So let's say 100. Right? Blood pressure, skin thickness, let's go on average. Skin thickness units. Let's say skin thickness units, right? I see the unit of skin thickness there. Milliliters, okay? Makes sense. It's obviously not centimeters. Let's say 40 seems average. 40 insulin. Insulin. A hormone that lowers the level of glucose, a type of sugar. Okay, lowers the level of glucose, so it's battling our glucose. It is made by the beta cells of the pancreas and released into the blood when the glucose level goes up, such as after eating. Right. So, okay. Lowers level of glucose, nice. So insulin average value. Let's see what the average value is like. Okay, 5 to 15. What's this? I think this is new. Yeah, I've seen that value before. New something. Micro international units per liter. Wow. Okay, micro. That was physics new. Right? Micro international units per liter. Wow, that's a lot. That's a lot. So 5 to 15. So okay, with normal fasting insulin levels for healthy adults generally falling between 2 to 25 micro international units per milliliter. That's weird. So 2 to 15, and we have 207, 43, 130. Oh my god. That's that's crazy. It might be in another unit though. I'm not so sure. So it depends on data set. So I guess when downloading data set, we just need to understand the units, the values, so as to inform the users about this information before putting in any value of their choice. Alright. So code. So yeah, I guess that's everything they have there. Not a lot of data. Alright. So to just specify to express the insulin level in blood, express the age, not enough information if you ask me. Okay. So let's just go with text, right? BMI, body mass index. So I'm familiar with this one. So it's basically just weight over height square. So it's just basically, it's just a number that basically checks your body mass index level, whether you're overweight, underweight, stuff like that. So yeah, I think from anything before 18 is underweight. So let's just say BMI. Okay, for you guys that don't know BMI. So body mass index is a measurement of body fat based on the person's height and weight. As I said, weight over height square. Alright. So let's just say like body BMI range. Okay, that's for men and for women. Serious. That was the same. So underweight is anything below 18.5. Healthy or normal weight is 18.5 to 24.9. Overweight BMI is 25 to 29.9. So they're all values basically, right? So your weight in kilograms, I think. So let's check the units. I don't think I'm sure about units. So yeah, I know the weight is in kilograms and heights in BMI units for weight and heights. Let's see, units, uh, pounds. I think you can just basically change kilograms and heights in meters, right? Kilogram meters to basic, okay? So if you are like, let's say 6 foot, right? Let's say 6 foot to meters, 6 feet, sorry, 1.82, right? So by 3.82, 3.281. Okay. Let's just say an average somebody that will be right, let's say 25.5. So we're going on the healthy side here. This person shouldn't have diabetes from what I'm putting. So degree pedigree, diabetes pedigree function. We checked this earlier on based on the age, based on family history and everything. I wonder how they got that. Let's see how they generate this value actually. Diabetes pedigree function. Here we've checked this, we've checked it. How is it calculated? Let's see, function calculated. In the PIMA Indian diabetes data set. Oh, I think that's the same data set here. Is it the PIMA Indian diabetes data set? I don't think that. Okay, yeah. In particular, all patients are females. Obviously, that's why the pregnancies included. Males can't give birth, right? So all patients are females, at least 21 years old of PIMA Indian heritage. PIMA Indian heritage. So it's basically Indian women data we're using to generate. So I don't think that's quite fair, but still is data set. So you can just align it to Indian women, right? So Indian women, but still it's a data set and we're going to work with it. So let's just go average, let's say 0.7, right? 0.743, something like that. Age, let's say 30. You're giving birth twice. I would say you're 35. Alright, seems okay. You are okay. So now let's run this. See what we get. BG is not defined. BG. Oh, on this second line here, I said BG instead of BP. Passing it as my predict function. Run it again. Run that guy again. Run this guy again. Or are we getting another error? Let's see what we have now. Okay. I think it's something with our predict method there. Logistic regression was fitted with feature names. X does not have valid feature names, but logistic regression was fitted with feature names. So I guess it's time to debug. Reshape your data using array or reshape if your data has single feature names, if it contains sample. Okay, so after quite the time spent on debugging, finally deduced I was supposed to pass a 2-dimension array. So I needed another what? I needed another basically square bracket around this, alright? So it needed to be 2-dimensional. So just run that again. Okay, yeah. So it needed to be 2-dimensional, okay? So since we have more than one value, so predict. Now let's run a function again. You don't have diabetes, thank God. So remember, we used balanced values, remember, right? Because it's quite basic to average, nothing too big, nothing too small. So, just a standard healthy young Indian woman, right? So you do not have diabetes, thank God. Right? So now let's check the accuracy of our model. You can see our model works well. How accurate is it? Is it just telling me what I want to hear, or is it actually good? Right? So they're called metrics. So metrics are basically used to check how well our model performed, right? So we have different metrics for classification problems. We're not going to go deep into it right now. Just going to look at our accuracy. So we have precision, recall, F1 score, stuff like that, right? It all comes from Scikit-learn metrics, right? Everything revolves around Scikit-learn. So from Scikit-learn, the metrics imports what? Imports let's say classification report. So we have confusion matrix 2, which we'll be looking at soon, probably in the next video. It's quite easy, right? It's basically how many we got, how many we missed. I think we should even look at it right now. So sorry, classification report, comma, confusion underscore matrix, right? So import those two guys, then print confusion matrix first. Let's print our confusion underscore matrix. So okay, it's basically a table, right? So let's see. Still running. Oh, sorry. I just printed confusion matrix, but I didn't specify what. So basically, I want to compare what? I want to compare my actual Y test, right? So I'm not checking the accuracy of this, right? I'm checking the accuracy of this guy here, right? So I want to compare my actual Y test, which is my actual results, to what I got as my prediction here. Remember, my predict, sorry. I predict is this guy here, is this whole value. And this whole value is basically what my model did by itself to what was actually in my data set here, right? So I'm not checking the accuracy of this one I just did here, right? It's just a single value, right? I want to check a lot. So my actual Y test, which is what I splitted earlier on, if you remember. So that should be around 600. And this predicts, which is also probably 600 values. But you can check it if you want. So confusion matrix of those two guys. Okay, so now this top column, the confusion matrix basically is in different formats, right? But this guy up here represents predicted value. This guy represents actual value. So this guy here is actually true positive. The amount of truths, which is 1, right? Remember, 1 represents true, 0 represents false, right? So the amount of truths that are correct, like they're actually what is in the data set, and my model got them. So out of, if I add everything together, okay, is it? Okay, 600, yeah. Remember, our Y test is 600. 600, right? 600. So let's deduce that. So out of 600, 351. Well, let me comment, right? So 351 of 600, our model said were diabetic, right? Diabetic. And they actually were, and they were, right? So true positive, that's what true positive means. It's true and it's positive, or it's truly positive. Like, oh yes, they are truly diabetic patients, right? So 351 out of 600. That's a good value, right? So diagonally down here diagonally down here is our true negative. So diagonally down there is our true negative, meaning 132 out of 600. Our model. So I didn't put model there. Our model said were or people were diabetic. So I think where it's right English. Said were diabetic, right? Our model said were diabetic or were not, sorry, were not diabetic, right? True negative diabetic, and it's correct. And it's correct, right? So they were truly not diabetic, right? They were truly not diabetic people. So 132 of them were not diabetic. So it means we actually have more diabetic people than more non-diabetic people, right? So top right here, we have our what's false positive. So here we have true positive. Beside it, we have our false. No, sorry, we have our false negative up here. True positive, false negative, false positive, true negative. Okay, so up here we have a false positive or false negative. Sorry, I keep switching that up. So that's false negative. For false negative meaning 38 out of 600, right? 38 out of 600. Our model said were what? Negative, meaning they didn't have diabetes, but they actually did. So that's very wrong. False negative. Our model said they didn't have diabetic, but they actually did. That's a type 2 error. Alright? So it's a type 2 error. It's a kind of error. We call it type 2 error, right? So it's false negative. FN. Right? So our model said 38 people didn't have diabetes. False negative, right? Our model said they didn't have diabetes, but they actually did. So what? That's very bad. False error. Type 2 error, sorry, false negative. Right? And 79 people out of 600, so now women, right? Out of 600, type 1 error. So this is a false positive. Our model told them they had diabetes. False what? False alarm. Must be scary. This is type 1 error. It told them they had diabetes, a false positive, but they didn't actually have diabetes, right? So false negative is you were told you had, or you were told you didn't have diabetes, but you actually did have diabetes. False positive, you were told you had diabetes, but you actually don't. So our model basically missed this. He missed 79, he missed 38. He missed quite a lot. So the true positives are what he got correct, and the false are what he missed. So 13, 38, 79, that's quite a lot of data. So our model is not very, very accurate if you ask me. So now let's check the percentage. All this is just statistical information. So to best remember our confusion matrix, you can see it like this. So come down here. So that's a true positive. We have, sorry, true positive up there. We have a false, fuck, true positive, true negative, false negative, false positive. Okay, so we have our true positive there, false positive, right? Then true negative, then we have our false negative, right? Okay, so yeah, we basically have this as a confusion matrix, easy to remember. So we just change it from being a code. So come up here, change the cell markdown. So it's more of like, or it's documentation, so too big. So the hashtags actually matter here. Just add 3 to make it smaller. Make it 3. It's too big, but just can manage it out. Okay. So now let's check our classification reports. Basically just different values, but it's accuracy we're basically looking at. So the same values there. Change the function to classification. Underscore reports. Run. So you can see multiple things. But this is majorly our accuracy here, 0.81, which is what? Which is 81%. So if you ask me, 0.81 out of 1 is 81%. It's good, but not too good, right? So you can see our 389, it got correctly. If you add it together, right? So the people that didn't have diabetes, I think 0, right? So the precision for the people that didn't have diabetes is 2%, people that actually had 78%, 389, 211, stuff like that, different values. Okay, so our model is 81% accurate. Okay, so yeah, that's basically it for the project. So yeah, let's go over it one more time. We ported NumPy and Pandas, two foundational packages. We didn't really use them much. We didn't use NumPy at all. We didn't use NumPy at all. So, but NumPy is quite important, but we didn't use it at all. So in case we wanted to get the main media mode stuff like that, I would have used our NumPy. Now see, it's a model too, so we basically relied on Pandas, read the CSV. So basically every other method here, the reason why we use every other data framing object method is because of our Pandas, right? So we read our CSV file first, where our data set is. We printed it out, we check the head. Remember, the top 5 by default, you can specify how many you want. We infoed it, we described it, then imported our logistic regression algorithm, which is an algorithm under supervised learning, right? So it basically helps us classify data true, false, 1, 0, stuff like that. We splitted our data into training and testing data set, right? We dropped outcome, we used outcome, train test split here. We checked the head again, we fitted it to actually train our model, right? Then we predicted, then we wrote a nice little function to determine if you have derivatives or not. Simple if and else statement, right? And remember, pass it as a two-dimensional array when you're passing more than one value. Okay, so yeah, simple project on what's diabetes. So if you're new into machine learning, I hope this will help you kickstart your journey and yeah, do more projects and enjoy the world of AI and machine learning because it's the future. Thank you for watching. Make sure you like, share, and subscribe. I'll see you in the next video. And remember, part 2 will be a graphical user representation of this project here. Thank you for watching once again. Make sure you like, share, and subscribe once again. See you in the next video once again.